All right, let's do it together. That's gonna help a little bit. A not, B not. Let's consider this signal as one entity, right? We're not adding inverters in front of it. Let's just directly use that signal, assuming it's available. And for this block, and these blocks are in series, so we are expecting one on the top, one on the bottom. And for each of them, they are a AND logic under the bar, so they should be parallel PMOSes. A not, B not, A and B. Okay. And for the NMOSes, it's OR logic, so these two blocks should be in parallel. Okay. And because that's the AND logic, so these two should be in series. Okay. So the entire circuit here is what? Logic. What is the output here? What's the logic expression? Do we? We got bar on top already, right? So the logic here should be able to implement that logic, entire logic over here. It's like the NAND gate, okay? It's just the nature of the circuit design for this type of schematic. Right, for this one, it is A and B not, right? Since A, B are in, it's an AND logic to connect A and B. So we need the parallel PMOS on the top and series NMOS at the bottom. And the logic here is already, it's going to it's an inverted result of the AB AND logic. It has a bar on the top already. Okay, same to this one. So we are looking at the logic at the bottom of the bar, but eventually it has a bar on the top for the result. It's the nature of the circuit. Why? Because if you give a zero, it opens up the PMOS and connect to one. So you give a zero, not this one exactly, but what I'm saying is like the inverter circuit. It's a CMOS logic. PMOS is always connect the result to VDD. So whenever you turn on the PMOS, you have to give a zero to it. It's always inverting the circuit. Okay. So what is the result here? What's the logic? Yeah, A XOR B. So this logic is called an XOR gate. The entire circuit here is the XOR gate actually. If you put into icon and leave the ports available, that's the XOR gate. You are saying there are four inputs. How this becomes the XOR gate? How to convert into XOR gate? It's basically you have how many inputs for the XOR gate? How many inputs are there? 2. But I got 4 here, right? Add inverters. So you do have A and B as 2 signal inputs, right? For the XOR gate. Okay. Right, like that. But the 2 signals are being inverted first and then being fed into the gates over here. If you compare to this one, so the entire XOR gate has only about 8 transistors. If you don't consider the inverters, which are simple, there are 8 transistors. If you just look at the AND gate itself, just one gate, it has about 6 transistors in there. Okay, so this can be because you have less number of transistors, so less parasitic capacitance because all the gates are capacitors, so which will reduce the time delay and also reduce the footprint of the circuit. So how do we design the stick diagram for this circuit? I'll give you a few minutes to draw yourself instead of I'm just person always talking. Give you 2 minutes to try it.
I got a bottom part right.
The bottom is easy, right?
Yeah.
Anyone can draw the bottom part over here real quick? Yeah, let's do it. So we can keep adding onto the stick diagram. You guys, as a collaborative work, so you can finally make it work. Even just adding one transistor or one line is helpful. Okay, so everyone can, can be a judge here, see if they're making it correct.
Are the O's NMOS?
NMOSes. Yeah. Okay, let's do it. Yeah, let's see if we all have A and B here, right?
Yeah.
So as XOR logic, we definitely know that should be 0, 1, 1, 0, right?
Yeah.
So if both A and B are zeros, you got 2 1s here, right? So it's blocked. But these two are on. So they're getting a 0 verified, right? The next one, 0, 1. Okay. 0, 1, which means one of them are on, right? And same here. So it's connecting to the top. But because one of them is off, so none of these two are on. So I got a 1 verified. Same to this one. 1, 0, 0, 1 doesn't matter. It's symmetrical, right? Interchangeable for A and B's. And for both ones, this is definitely on, right? So it's definitely being pulled down to the ground. And but not here. Because even though oh no, these two are off. But these two are on. It doesn't work at all because it's blocking the connection between the ground and the output. No, the VDD and output. Because these two are off and they are in series, right? For the last one.
Yeah, no.
Okay, verified, right? So it works.
So how do you look at that expression and you just know that you need to do it opposite to the PMOS and the NMOS?
Yeah, that's the experience came from this. I think that at the very beginning when we designed the NAND gate and NOR gate, we find out that's the way we have to do it.
And it's switched like that because the property of PMOS is passing the 1 when 0 is at the gate.
Yeah.
Okay.
Yeah.
So it's sort of like automatically incorporating another bar into that expression.
Yeah, because PMOS is connected to the VDD and you need a 0 to turn it on.
So in that sense, you could think about it as when you're doing the layout with the PMOS, you just incorporate the top bar and not the whole expression.
You don't look at the bar at all. You just need a bar to start with, right? You have a bar and then you look at the expression below it. You don't need to consider the bar on top anymore. But you do need a bar to start with, okay? If you don't have a bar on top, you should be nervous about it because you cannot start working on that process. So I have to make a bar on the top first and then just look at the bottom logic for the design, right? Makes sense? And we find out this conclusion from here, from the truth table of NAND and NOR, all right? Okay, then we find out a circuit like that. And since we know that works, then eventually we directly just skip that truth table and it's also impossible to look at the truth table of the complicated logic and design circuit from there. So we skip the truth table, but since we know the conclusion already, we just directly look at the logic expression. And then we know it's going to work. If you want to verify it, you can still go back to the truth table and verify it like this, right?
Yeah, that one. It's just confusing to think about how the wire.
Yeah,
It's like harder to
yeah,
think about.
that's right.
And
Yeah. Always think about don't think about the logic, but always think about the structure of the NAND gate and NOR gate. Because that covers both cases.
yeah.
Okay, so it's just like the NAND gate looks like this and NOR gate looks like this, right?
It's just nice to understand
Yeah, yeah,
like kind of
yeah, that's right. Okay, let's look at another example like this. Schematic and layout. Can anyone start with the schematic first?
Schematic first.
So the OR logic has to be implemented by series PMOSes on the top and parallel NMOSes at the bottom. Just think about the NOR gate, right? And then these blocks is being ANDed to D, right? So D will be, for the PMOS part, right? So D must be in parallel with that block for the PMOS. And then NMOS, D is going to be in series with everything. Can we start drawing the schematic on the board?
schematic.
Yeah, draw whatever you can draw, okay? Schematic or stick diagrams, whatever. Just finish as much as possible. No, the AOI logic, not the gates. Sorry, you asked with the gates, not the gates.
I'm not
Yes.
I need to think about that.
Uh-huh.
So that was easy.
So for the OR logic on the top, right? Think about the NOR gate. It's like this, right? So you need a series PMOSes. And then this one is a NAND gate logic. It's an AND, so it's forming a NAND logic. So it becomes this. The PMOS part on the top is getting wider, so they are in parallel with this block, right? Can anyone start from here?
Start from this schematic and keep drawing the bottom one.
I don't know, get lean out, I just don't know how to make it all the way.
Try it. Doesn't matter.
See what.
I mean, it's good to.
I'm down just linking the case together.
Yeah, it's good to expose as many problems as we can in the class, so you guys are not making the same mistake in the quiz or exam. That TV doesn't work. You have the gate level circuit.
That's a gate level.
So we're doing the AOI logic, right? So doing the not the gate level. This is pretty much the gate level because these are individual.
That's right. I mean,
These are these PMOS on the top. PMOS is right on the top. So who can do the NMOS at the bottom? Connor?
I think I have it.
Yeah.
I definitely just see that. There's yours.
Uh-huh.
And we're gonna do this. Don't know that this is completely right. Like, well, I can choose something.
Yeah, so the schematic looks right.
Doesn't have.
Yeah.
Let's see.
Yeah.
Maybe?
Yeah. Who's going to work on the stick diagram?
I'm going to start with something. So first, to draw the two rails. Okay. 4 transistors, so 5 nodes. Right? 1, 2, 3, 4. We got 3 in parallel, 3 in series, and 1 in parallel. We got 1 go that way. And, what is a better way to do it? I believe you got maybe more traces in the top instead of at the bottom because you may route other traces in the middle. So I'm going to do that. No means one, right? Yeah, I just need one. That's right. That's right. Oh, I was thinking this. No. Right.
We can work on the bottom part.
So if you were just drawing A or B or C with a PMOS, it would just be the 3 in series.
Yes. Yes. Wait. That's right.
No, does it,
But A or B or C.
that's why I'm getting confused on this.
Because you are not, you have to look at the truth table. It's not A or B or C. It's actually, you are looking at the unknowns, because most of the cases, A or B or C is giving you a 0. Because if one of them is 0, it's hard to explain that using words, but just look at the truth table, it's going to work out. Don't worry, don't think that complicated about the circuit,
I
right?
just don't get how putting 3.
So the way to verify it is not like you are thinking like PMOSes are in series for A or B or C logic. The way to verify it is eventually you go to the truth table and then put the numbers in there to verify it, right? But physically, you are not using the OR logic for the PMOS. Because A or B or C, one of them is off, the entire wire here is not being shadowed, right? So nothing is going to communicate through this line. But others may, right?
Oh wait,
This will.
that does make sense because it's inverted.
Mm-hmm.
So if any of them are written high, it's low, which makes sense. Because then you invert that, and if any of them are written to 1, if A, B, or C is written to 1, then it's inverted. It returns 0. No, that makes sense.
So it's not being used, as what are saying. So if one of the PMOS is in that line, if one of the PMOS is not on, that line is not being used at all.
Yeah, it makes sense now. It just keeps
Yeah. Can you work on the inmost part? Yeah, no worries, just try it. Yeah.
These two are parallel.
There's a middle line on the top here.
What is it?
It's very close, actually. Let's put it that way for now. Let's see if other people can figure that out. So we have 3 in parallel. So 3 parallel transistors can be a little bit challenging sometimes, right? How do you draw 3 transistors in parallel? So what is this? Okay.
Can you just, um,
because the 3 transistors are in one line, so I have to redesign the circuit carefully in order to make them in parallel. There are some ways that you can remember it. If you have 3, doesn't matter, it's almost or PMOS, right? Like this. How do we make them in parallel? It's basically just this, right? Always. So 3 parallel transistors in stick diagrams, it's always being drawn like that. Why? You see that this is the current flowing here, right, into it. And then, wait, that's correct. Oh yeah, it goes this way, the first one, and flows to this channel, the second one, and then the third one, right? Okay, and then merge here and merge here. So it's eventually become one node.
That's right.
Hmm?
Or what I did is
So what was the problem from the first drawing here? I think Noah drew this, right?
yeah, is that right?
What was the problem here? It doesn't have a connection to the ground, right? And second, the middle transistor, it flows to here, but so which one you want to connect to the ground? If you do this, then this becomes what? What's the schematic of this kind of layout? So it has one signal from the top, right? And being split into 2. So that's the first one, right? Which is this guy. Okay. So and then ground it. And then this channel flows through 2 transistors in series into ground, right? Okay, and then this wire getting split into the other one in parallel over here, which is D. So that's the schematic for this layout, right? Is that correct?
But then it would be possible to short it to ground when D is low.
Short to ground when D is low. Don't think about logic anymore, please.
But it wouldn't work, right?
Don't think about the logic. Just look at the physical layout or schematic. Okay.
So that's right.
No, this is not right. This is this.
Okay. Okay. Yeah.
But
yeah.
we need 3 parallel resistors, right? Transistors.
Oh, okay. I thought you were saying that. Right.
No. So the 3 here, they should be all in parallel, but 2 of them are series in this case. Okay. So what can we change here to make it work? So definitely this one shouldn't be shorted to that node, right? It should come just to here probably. And then do this. Remember the pattern here for 3 parallel transistors. You just do this. Remember that pattern? Okay. That's why I did this. Okay. It's going to give you 3 parallel transistors. Okay, that's why I do this. Right? Okay, and now let's see. This becomes the output. There's probably still a bug here, but eventually this is all the current merges to this node and go to ground. Is this still correct? No. Because this node, if you look at this node for the NMOS, right? Look at here. This node shouldn't be grounded. No. So that's why this node shouldn't be grounded. So we have to draw it in a different way.
So how? You can do it?
Is to go through T to ground, right?
Yeah, it goes through D to ground. That's right. Can we still do it? So 3 parallel transistors.
What was wrong with what you had before?
So can you just unground it?
Yeah.
And have that far ungrounded?
Oh. Still do this, right?
Yeah.
And then what?
And just ground it.
This. Aaron, oh, it works. Okay, I'm gonna let you label the A and Bs. Who can do it? A, B, C, Ds. Signal lines. Very close, right?
It's just left to right. A, B, C.
I'll let you know. You can let me know, actually. So what is this? So signal line from the top, right? Looking at that one. Definitely this must be A, B, C, C, D, right? Okay. What about this one? Yeah, it's in parallel, okay? A, B, C, doesn't matter. And D. Easy. Okay? I'll give you one more example. So I'm trying to simplify it a little bit because I can definitely combine some of the terms over here. Maybe AB or A or B, C. So AB definitely will be, it's like a NAND gate. Think about the NAND gate shape, right? But eventually it's OR logic, so they have to be on the top and bottom. So it's like A, B, A or B and C, so C must be here. And A or B, okay, what about the bottom part? What kind of, for the bottom part?
Good job. Yeah. Think about the stick diagram, and we can work on the stick diagram on Friday. Okay. Take a picture of this if you want, and it's due next week, I guess. Let's take a look at it.
I thought there's one due this Friday, but it's the same thing as the next.
I refresh the browser. I know. No, refresh it. I think I changed everything on over the weekend. Let's see. Let's take a look at it really quick. So I'll give you one more example, and then I'll let you draw the stick diagrams by yourself. Let's see if you can do it. So remember for example, you are asked to design a XOR gate. It's A XOR B, A B not, or A not B, right? Layout. What's the first step you should do with it? Remember, all the stick diagrams comes from the logic with a bar on the top. So does this one have a bar? No. So you want to add a bar on the top. Remember, the XOR logic is the inverse of the XNOR logic. So this equals A not, B not, or AB, right? And not. Okay. We are basically designing a circuit, transistor circuit first. So I have to find out the AOI logic and draw the schematic in transistors, and then convert into stick diagrams. There are two components in the process. So the first step is to draw the transistor level schematic. Okay. So before I move forward, I'm going to ask you one more question. Why do we want to do that always? For manual laying out the circuit. Why we not just for this guy, right? It's basically A B not. Okay. And then A not, and this will be B, and you OR, right? So this is XOR basically. Well, we are taking the effort here. I know most of you guys know that, but just, no, why we, so from here to here, that's a schematic, and then we just convert into the layout. So we know the gate, this is the AND gate, which is this.
So you're saying why you draw this schematic?
Yeah, why do we do that? No, why we are taking the effort to draw the transistor level circuit instead of using the gates. Because we know the AND gate, this is NAND gate. So AND gate is basically just the inverting result, right? So that's the AND gate. That's the AND gate, input, output, okay? Yeah, that's right, yeah. So you can reduce the number of transistors being used and reduce the footprint of the circuit on the chip, okay? Which reduces the footprint, but also the power, okay? That's why we are taking the efforts to do this. If you, after you drew the circuit, the transistor level circuit using the AOI logic, if you compare it to the gate level circuit, it's way smaller than that. However, in electrical VLSI or in Cadence, It's not doing the optimization for you. It's basically just using the gates to make the connections. But when you are designing an analog circuit, which has a digital part in there, so I have to manually lay out a lot of things. So in that process, you are able to, or you have the chance to manually draw the transistor level circuit instead of using the gates, because you are manually designing it or optimizing the circuit. But not in the huge level digital circuit design. So the EDA tool is going to synthesize everything for you. Okay, so now we know the extra logic is the XNOR with a bar on the top. So what's the next step? So for the AND logic, you have two PMOSes in parallel on the top. Okay, and these two blocks are being ORed, so have these two blocks has to be in series on the top for the PMOSes. Okay, I'll let you guys do it yourself. Take a few minutes and draw it. It's okay if you cannot finish it. So I'm gonna draw the result in a few minutes. Yeah.